Welcome to the video Isotherming, Austempering, the lower hardness grades and machinability. We have seen in the previous slide how is important the austenitizing temperature and the need that is selected in order to guarantee a sufficient driving force for the reaction. But this requirement is not in agreement with another requirement. The other requirement is quenchability. You remember that for ADI, for the asperitic reaction, we need to avoid the paralytic nose. And avoid the paralytic nose requires alloying. One very important alloying element is carbon. So as much as we raise the austenitizing temperature, the more carbon we put into the austenite. And so we increase the austenite stability. We increase the material quenchability, the possibility to avoid the paralytic nose. So increasing the austenitizing temperature helps in reducing alloying. That is beneficial for cost, but is also beneficial for segregations. Okay? So we have two requirements that are in conflict. Increase the temperature, save alloying, but at the same time, you reduce the driving force. So with an excess of austenitizing temperature, you risk to have unstable austenite. And this is especially true at low grades, when you need to raise up the austempering temperature. So if I have low grade, high austempering temperature, to get a sufficient driving force, I need to reduce the austenitizing temperature, but in this way, I reduce quenchability. And so I risk to have a perlite into the casting, or to have an excess of alloying addition. This was the original problem of ADI development. In fact, at the beginning, ADI grades was typically high strength grade, dedicated to gears, to wear resistant parts, called as unmachinable after retreatment, hard materials. The solution to the problem of low grades has been provided by Dr. Milberger with the Germanite process, which was the essential observation of Dr. Milberger. It has been that moly is not a carbide stabilizer if manganese is low. So the Milberger patent was essentially ADI with the low manganese content. Then, with the low manganese content, you can add moly as hardener at the level you need without promoting carbides. On the other hand, moly is not dangerous for the chemistry in segregations. Moly has another bad aspect that is promoting porosities in the heavy sections. So moly is a good hardener, it's expensive, but it's a good hardener to increase the quenchability in the heaviest sections, but we cannot use too much moly if we wanted to avoid porosities into the larger wall thicknesses. For this, the low grades has been invented. The process to produce the low grades has been invented by Dr. Milberger in the 70s with a patent called Germanite that was licensed firstly for the lowest grades to the Foundry Katrineholm in Sweden of SKF Group for producing axle bearings for high-speed trains. And then in 85 it was licensed after 3 years of studies and tests to Zanardi Fonderie. And so at that time started the so-called machinable ADI that was dedicated to the low grade 700, 800, 900. So the Germanite patent also included the highest grade, and like 1050, 1200, 400, 1400 as usual. But it was a typical process. But the main focus of Germanite was the low grades. And our company has been successful in developing these low grades on the market as machinable ADI after the treatment. And this has been a paradigm that has been also followed by SAE, the Society of Automotive Engineering, with the grade AD 750, and that have been developed on the market, and now is a common process for professionals that want to apply those rules. But these rules have also a limitation. Cannot be applied to a too large wall thickness, because if we require a moly addition too large, we have the risk of porosities into the thickest sections. For this reason has been invented the IDI, isothermal ductile iron, that having no alloying, then no segregations, is able, with a ferritic pellitic structure, to reach nearly the same properties that we should have with the ADI in the large thickness for low grades. So IDI is completing the low grades ADI in variable and large wall thicknesses. In this way also the alloying is saved, because there is no additional cost for alloying, and we have a uniform properties, a good soundness in all the sections. But we need to remember another essential, mandatory requirement, that is the process robustness. We cannot produce good austempered ductile iron if we are not starting from a proper casting as in the scarce condition, and if we are not doing the heat treatment with the proper devices. Austenitization needs to be performed into a austenitizing chamber that ensure uniformity in the mass. Then the transfer between the austenitizing chamber to the salt bath needs to be made in a way that does not lose too much temperature in the batch. And then when the batch enters into the bath needs to be large compared with the batch. Needs to be agitated, possibly added with water, in a way that the cooling curve into all the section of the casting is as quick as possible, limited only by the heat transfer inside the casting, that we cannot do nothing, can do nothing about that, because inside the casting we cannot. But we need that the salt is able to achieve its own temperature on the casting surface without any boundary, without any transitorial temperature transitorial between the salt and the casting. This is very, very, very important. This, if this requirement is fulfilled, we are able to reduce the alloying amount for a given thickness, and so to achieve the best properties and the stable austenite. If the austempering plant is not proper, it is impossible to get stable austenite and a machinable casting after treatment. Very important is also the process control that is made by tensile test that now we analyze in a new way with using Voss analysis to check the austenite stability, or traditionally with the heat tainting where the blue areas corresponds to unstable austenite transformed into martensite.